that if I have access to the chat, and then we continue. Okay. And chat. Okay, perfect. Yes. Right. So where we were with the machine learning toolbox, and let's open it quickly again. And we wanted still to see how it works also for Sentinel-2 data, right? Since nowadays that's the most common data freely available. So I go back again to inputs, and I will select. I also prepared a folder with Sentinel-2 data into data for ARTMO, Sentinel-2. And here we have our field data that was collected within the context of validating the official LAI product that is available within the Snap Toolbox. Again, so these are LAI samples, the first line, and underneath are the spectra. And we, as we discussed before, also we added some bare soil because I want that the model works not just over vegetated surfaces, but also over non-vegetated surfaces, that you really can map the whole image. Good. All I have to do is to define what line is our variable, LAI in this case. So we select, also we add the units, and we have to tell from where the spectral data starts. So this is just Sentinel-2 data taken from the 10 and 20 meter bands. We have only, in this case, 11 bands available. Basically, it's all the 10 and 20 meter bands. Okay, so we click on import, and we can quickly run some models because it's actually a small data set, just a few bands and relatively few samples. This time I will add some more machine learning models just for you to know. So also random forests, maybe of interest is also neural networks, also these Gaussian processes, kernel-rich regression. And this will be the first step, and then afterwards, where is the, oh, afterwards, I don't see the neural networks now, but it should be somewhere. Afterwards, I want to show another optimization trick that's available there. So let's just keep 70% for training, and the other is for testing. We click on done, and we start running it. I'll quickly give a name. And it starts now evaluating all these selected models. It takes a bit longer now because also random forests are included. And in this case here for this data, random forest appears to be top performing. So what I discussed or told before, it's really also dependent on how the algorithms are defined. So in our case, random forest only generates 100 trees. I've seen papers where it's done much more. In other computing languages, it's also more optimized. So you always have to be careful with this kind of results, as it really depends on which language and how the models are tuned. Interestingly enough, also here, our Gaussian processes is not so top performing, but other models seem to be performing better for this data. I want to show Sentinel-2 data for something new that I think is very useful. And I will show it with Sentinel-2 just because it has few bands and that goes really fast. And it's an analysis how to see the most important bands of your data. So what are the most sensitive bands? With Sentinel-2, when you have only 10 bands available, maybe it's not that important, but imagine that you have hyperspectral data available. You really would like to know what is the sensitive region for your variable of interest. And to do so, we will make use of this band relevance of Gaussian processes for doing ranking. Basically, the largest sigma value means the least important band. So if we remove each time the largest sigma value, we end up with the most relevant bands. And this is our band analysis tool that I will quickly run. It will go fast so that we can see the relevant bands in case of Sentinel-2. Again, Sentinel-2 is not the best example, but when you do it on hyperspectral data, it's really nice to see what are the regions that are the most sensitive for your variable of interest. So I select only Gaussian processes, and in band tools, we have this GPR band analysis tool available. We will select it so based on ranking of these sigmas, and to make it a little bit more robust, I will combine it with cross-validation. So we use 3K and we click on DOM and we run it again. So validation, let's call it GPR BAT for LAI. And then afterwards, let's inspect the bounce relevance analysis. So this will take a little bit more time because now we start first with 10 bands. It removes the least contributing bands, 9 bands, again, removes the least contributing bands until finally only 1 band is left. Okay, well, as always, it shows the top performing band, but we have this option to query out the database all the models. And now we see the performances. And this is actually a message I would like to give, that even though when you have multispectral, but much more hyperspectral data available, it is not that using R bands leads to the best models. In fact, we have this problem of multicollinearity, which means that many bands, they contain the same kind of information. And when you train with the same kind of information, it just complicates the regression model. So it's much better to first simplify it by means of reducing bands or transporting it to a lower dimensionality by means of PCA also. So 4 bands appears to be the best performing, 5 bands, 6 bands, but 10 bands not. And of course, using 1 band or 2 bands, what is commonly done with vegetation indices, are also by far not best performing. Now let's have a closer look about what are the best performing bands. Sorry, I need to select this guy here. And a new window will appear if I run it. And yes, I was running it for the chosen statistics normalized root mean square error. I will change it, the statistics, to R squared. So I will close this and repeat it quickly. Just for you to realize that how the performances work. So when we have 10 bands, or when we have 9 bands, or 8 bands, or 7 bands, actually until when we have 4 bands, the performances are exactly the same. So it's really not needed to have that many bands. You just need to have the right bands. 1 band, the correlations are pretty bad. What then of interest is to see what are these bands. And this is in the other window that appeared, where we see the wavelengths from 10 bands onwards until finally 1 band. And then for LAI, and we have this discussion. So the most important band for LAI appear to be in the swirl, and the very last new Sentinel-2 band is swirl band, and the second most also in the swirl in this case for this data. When we're having 3 bands, then also the band in the red appears to be important. But in this way, we can see what are the relevant bands and their performances. So personally, I would go just with these 4 bands. It makes the model much lighter, and there's no need to process all the data. So with these 4 bands, one in the red, in the near infrared, and in the swirl, that leads already to excellent results. Again, it's a little bit a silly exercise with Sentinel-2, but when you do it with hyperspectral data, you really will see that using all the bands in machine learning will not lead to best results. Neither will be when you use only 1 band or 2 bands, as is commonly done in vegetation indices. With this, I want to close the machine learning approach. So again, you can click on map and then afterwards go to the next step and process immediately all your Sentinel-2 images. Let me quickly do so, just for you to see that the mapping still works. Sentinel-2 images are very heavy, a few gigabytes. We can process them. Here, in this case, I will just show a small subset of 400 by 400 pixels. But in ARTMO, in fact, the processing works in blocks, so not the whole image is loaded, it's just a part is loaded, it processes it, then the next part, and so on. So to avoid memory problems. So I just quickly run it, and right, there was an error appearing because I was not using the right ARTMO version, and I did not have the license installed. So luckily, I already believe I did already that mapping. I will quickly just show the map, and then to close, I would like to show you the vegetation indices toolbox because I noticed there was some interest in it on how to optimize vegetation indices. Right, so in the machine learning toolbox or in any toolbox, we also have these tools where you can view your maps, figures. You can do apply scatter plots where you compare one map against another one. Even also, if you have new data measured in the field, you can use here validation of new data of your models. So you can check yourself these options. If I will quickly open the Sentinel-2 final product, we can see again a very nice map. And also here we can have our absolute uncertainties, which are really low, so that's good. And then the relative uncertainties, where it shows again that the model was working best over vegetated areas, because that's where the model was trained for. Now that we see how this toolbox work, in fact, all the other toolboxes work in the same way. So you always have to go input, settings, validation, retrieval. So I can very quickly show you also the spectral indices toolbox because I think it's of interest to calculate not just the standard indices as was shown before, but in fact we can calculate immediately thousands, even hundred thousands of indices by combining all possible band combinations. So I load my data, and this time I will load hyperspectral data from HiMap, 125 bands. So we load again, this is fine. We define our variable. Let's stay with LAI. And in this case, it's line 3. Okay. We add, and here spectral data starts at line 7. Import. So with machine learning, we just have to select a machine learning algorithm. With vegetation indices, it's actually a little bit more complex. And it's more tedious because there are many more ways to optimize it yourself. It's a parameterized method. That means that you need to parameterize yourself. Parameterizing it in all kinds of ways. You need to decide on what is the vegetation index, what are the bands that you use, and what is the fitting function that you use. The way it works in ARTMO, we put in a few indices, standard ones, but it's not that we just will calculate NDVI. No, we will use the equation of NDVI and that to apply to all possible band combinations. And again, in ARTMO, you can select immediately different kind of equations. In tools, you can develop your own equation. And so far, these are just two band indices, but actually you can develop your own index with 3 bands, 4 bands, up to 10 bands, so that it does all possible bands against all possible bands against all possible bands. So immediately, hundred thousands of combinations, it calculates it, stores it into MySQL, and gives you the best performing results. To keep it simple, I will just show NDVI. So this is the equation here, and we will just use one fitting function. This also is important to realize. So far, in case of Matthias with the Nmap box, he was showing it with linear fitting function, but in fact, you can use any kind of fitting function, exponential, logarithmic, power, and so on. Polynomial to the second degrees or further on. Also in ARTMO, we have the option that you can add more equations in case you believe a third order polynomial is more powerful. You can add it yourself and also try that one. So what we do, NDVI with a linear fitting function, we keep our 70% for calibration and 30% for validation. So first it will use with the 70% of the data, try all these possible band combinations, Then afterwards, it will calculate the fitting function, and it will repeat it with the 30% to see if still the same results, or to verify, to see if still the same robustness is required, is obtained. So I click on done. Again, I give a name, HiMap, LAI, NDVI, and we did 70-30 distribution. So this went really fast, but in fact, it's more impressive when we see the results, because thousands of results have been generated, and it only shows here the top one, right? But I could easily say, give me the top 10 or top 50, for instance. And so immediately all the combinations are given. And this is for the validation data, but we can do also for calibration, although we are more interested in validation data. Again, we can have all kinds of options. For instance, we can first plot your index against your parameter. So this is, we see the equation, what the index, we have this linear fitting function. So we see the equation is given. And, but more interesting, I think, would be, again, measured against estimated. So how is it measured, and how the index was estimating it. But much more interesting, in my opinion, is the correlation matrix. So it gives the results of all possible combinations. Now, if I click on plot, now it retrieves from the database all these results, and will put it together into one figure. And here we are. Again, since I chose normalized root mean square error as statistics, I will repeat it because I believe it's more interesting to see with R squared. So let me close this one, select again, and run it, so that we see the results as R squared. That's a bit easier to interpret. And here we have. And so I believe Miriam was showing all of us yesterday this kind of graph. So we can, according to NDVI, for all these bands, we see immediately what are the most sensitive regions for the data that we gave. We have a highly sensitive region here in the visible, here in the red to red edge. But more interesting or more exciting is that here in the sphere, there is the most sensitive region. When we combine near infrared with the sphere, appear to be most successful in this case for LAI. And effectively, the best performing band combination was using 570 nanometer together with a sphere band. So that's in this region here. Afterwards, when you are done, when you decide, okay, let's try this index, so you can select it. It's being selected. You can do that for all your variables. You click again on done, and we go to retrieval again, and we do exactly the same steps. Also here in retrieval, you could also have decided calibrate yourself without validation, but since we do validation, the model is generated here. If I click on OK, I need to make sure I have the right image. I go to HiMap and the output, and it will process it super fast. This window appears in case that there may be some mismatch between the bands of the training data of the text file and the image, but probably it will be working fine enough. And now it's processing this HiMap image. And we can see we can get, again, a nice LEI map with reasonable values, although we see also there's some negative values. So the fitting function was not perfect. But this is the way how a map is generated with a vegetation index. This is a little bit all from the vegetation indices. I just want to say, so in tools, you can add your own equations. And we can say a new spectral index, and you say it should be with band number 4 minus band number 3, and so on. So in this way, you can generate, for instance, an index of 4 bands it will then evaluate all possible combinations against all possible combinations, so that you can generate much more powerful indices than these two-band indices, because we really should move away from two-band indices. Those were developed when we had just broadband sensors available, but now when you have so many bands available, that it doesn't make any sense to stay with just two bands. So I could do something like this. And then it will evaluate this 4-band index and search for the best performing spectral bands. Okay, this was all for the vegetation index toolbox. You may have noticed, if I'm here still, we have many more toolboxes and tools. There is also this lookup table based inversion. I will not show because this takes too long time. And we have also a numerical inversion toolbox. So you run the RTM against your spectral data. We are under the development of a classification toolbox where all the same machine learning algorithms are implemented. And so you can try also optimizing classifiers in this way. And then more interesting are tools. We saw already few. We have this spectral sample. Maybe this I want to quickly show because I had recently a question from the group of Andy, and now I have the opportunity to show it to him. So I select some data. And okay, this is fine. We need to say from where the spectral data starts. So in this line 7, right, that's the right data. And so here we have the option to resample your data that you measured in the field, for instance, towards a sensor of interest, Sentinel-2 or whatever. So there is this list of sensors. So you can just select the sensor you are interested in. Remember, you can develop your own sensors. And here are also the options to make your data more realistic towards real world situation. In case you had simulated data, we have this noise model where you can per wavelength add either multiplicative or additive noise. So you can really define how much noise. Typically there's more noise in the blue than in the SWIR. So you can optimize it, and you can combine it with smoothing, because with noise we have to be careful, especially with hyperspectral data. The data becomes super spiky when you add a lot of noise, and that's not like reality. So it would be better to add noise first and then smooth it in order that you have semi-realistic spectral data in this way. Another option here is adding filters. So if you spectral data, but you want to filter out after a certain maximum, you give a value and say, all those spectra that have with a variable beyond that maximum or minimum should be moved out. You can filter out NaN values or no values or negative values. So we can filter it. And I remember Andy or someone from his group asked me if there is a way that to fill up data within the spectra. For instance, the water absorption regions, typically you remove that, but you also want to fill it up in a way that your spectra stays complete, continuous. So you have an option here that you say, I want that the data is removed from a certain wavelength until an ending wavelength according to an interpolation method. And in this way, your data is filled up. So all these options are available here. That can be combined together with resampling towards another sensor. I think with this I will end. We have a few more advanced toolboxes, such as this emulator toolbox or global sensitivity analysis toolbox, but that would be, I guess, for a next session on the next summer school when we have more time. So with this, I would like to thank you all for following. And if you have questions, I guess easiest is just to contact me, or especially with the installing of the toolbox, because that's a little bit tedious. You have to install not only MATLAB, but also MySQL. Anyway, just contact me and I can help you. And with this, I would like to thank you for following still until the very end. And I would like to close, and I give the floor again to Enrico.